Hello, everyone. Today, we'd like to present our final presentation for our first project in Houston Omdena Local Chapter, discovering the relationship between crime number and weather in the Houston area. First, I'd like to briefly introduce our local chapter. The mission at the Houston Omdena local chapters include promote real-world AI through running open source projects, provide case study-based education, provide AI services to local AI enthusiasts and business around the world. We also have offline events, and our vision is to collaborate, network each other, and deliver projects with benefiting to our society and community. I'm the local chapter lead. My name is Xuanqin. And now we continue our project today. This is the agenda, including a brief introduction, data collection and preparation, explanatory data analysis, model development and inference, model deployment, and last, we will end with a concluding remark. Since currently in a metropolitan area like Houston, it faces rapid population growth, posing social, safety, and economic challenges. And we can see the total numbers of crime in a year gradually increase, and these are the projected value in the future. So it's already over 7 million per year. Moreover, the global warming adds to the complexity, leading to more unpredictable weather events. As shown in this panel, in the past 50 years, the average temperature rises 4.2 Fahrenheit degree. And will there any relationship between these factors? So the motivation of this study is first to develop time series analysis models that forecast crime numbers, and to investigate how much the predictive model can be improved by considering the weather information, and to understand how weather factors influence the total crime number and the specific types of crime numbers. And in the past studies have shown some examples, and the previous studied targets in the crime prediction models include the location-based, such as geospatial analysis, and the type-based. They study the likelihood of specific crime types with different patterns and trends, and their temporal prediction, such as the time series analysis, to forecast the future values of daily, weekly, monthly number of crime within a specific time period based on the historical data, and consider various time-related factors such as time, day, holidays, etc. And there have been suggested several common and correlated factors in crime prediction regarding the weather, including the temperature, precipitation, humidity, wind speed, visibility. Now let's move forward to the data collection and the processing.
Okay, so task one, we collected the data for Houston, Texas crime and weather data sets. So we are lucky at the very beginning of the project, we are able to locate the trustworthy data source of the.
See how to get the certificate. And this period. Before this, I want to show you how to do it, because with video is the translator workshop delivering the feedback. I will share with you how to do feedback. Please do it.
Weather data
and I show you how to do the
control crossing.
to get the certificate.
And we process the data for the crime data. Data sets were split
You should
into
to do the feedback, to give the feedback, you should go
different formats.
here in this page.
And also the
Minute.
is not clean, so we have to do try and error many times in the process. Then eventually we created 3 files, then merge
You should
into
go
one file.
in
Also,
from
original crossing weather data, those were the challenge for us is the free account only allow us to download the certain amount of data. So the many contributors downloaded the data. So this is a great.
you should go to here on the fundamentals of deep learning, and you will find feedback here.
Files and
Click on the feedback,
Thank
and
you.
you will get some.
Contributors and the team.
Click in it now, and you will start showing you the certificate process.
This is what we have
You can fill the
data
and send the feedback.
processing.
When you finish the feedback, tell me like this, I will count the number person.
Okay, then I will pass to the test 2. Udo, please.
Okay, so I'm going to be talking about what we did in the task 2, the exploratory data analysis team. So for this particular task, we had the goal of understanding the data sets that we were presented to from task 1. So we had to carry out an exploratory data analysis on the crime and weather data sets. We also had to identify the target variable for the model that was going to be developed. And in the end, we're supposed to produce a machine readable data set for the model development team. Here is our task approach, because we had various people working in this particular task. So we had to come up with a method that is suitable for the project, and also the task members to collaborate, learn, and contribute their expertise. So under exploratory data analysis, we carried out univariate data analysis. We analyzed individual variables. Then we carried out bivariant analysis. Then we had like data visualizations to explain the results that we found out. We also did some data cleaning. We took care of missing values and ensured that the format of the data that we were working with or passing on to the model development team was okay. Then in data transformation, we carried out some feature engineering and variable creation because of the nature of the data that we had and our goal. So we had to create some data we had to create from features from the features that were already given. And since we were looking at both crime and weather data sets, when we finished, we had to merge the 2 data sets together and came up with one single data set. And everything that we did in this task was documented, and we also used version control, which kind of like made the work easy. So for the univariate analysis, remember that we had both crime data and weather data. So we did like individual analysis on each of the data set before we merged the data together. For the weather data, we didn't have null values, and it's 7% of the columns were numeric. We had date columns as well. Then we also found out that the minimum humidity was around 18.1, while the maximum was 99.6. Then the minimum temperature in the data set was about 12.5 and the maximum was 110.5. The minimum wind was recorded to be 0.9 and the maximum was up to 40.9. Then one thing we noticed in the crime data set for the longitude and latitude variable is that they were only available from 2022 and it wasn't from the beginning of the data set, which is around 2010 to 2023 that we're looking at. Then we also noticed a significant change in the data format from 2018 to 2019. So I'm going to be sharing some of the charts that we provided while working on the EDA next. So here we're looking at monthly crime number history. I'm going to be using crime and offense interchangeably. It's the same thing, but in the data that we have, offense is the feature that was used there. So this chart is showing the monthly offense count on the y-axis, while the x-axis is showing the month and year duration. And remember that I said the data set is from around January 2010 to about May of 2023. So some of the things that we noticed is that offense or crime count increased after 2018, and we saw that this could be a change in the reporting from the Houston Police Department, where we got the data set from. Then we also noticed that offense crime increased after 2020. And one major event that happened around 2020 is the COVID-19 pandemic. So we noticed that around that period, there was an increase in offense or crime counts. Then next, we looked at crime counts by month. So here we have a bar chart that is showing the number of crime count or offense count from January to December. And the x-axis is the month in numbers, and then the y-axis we have the number of crimes or the number of offense. So during this analysis, we really didn't notice any significant difference in the breakdown of offense across the months. The month of February is low, and that's because we have fewer number of days in the month of February. It's usually around 28 days or 29 if we have any leap year. So what we noticed is that when we looked at crime count or offense count based on the number of months, we really didn't get any significant increase or decrease. Then next, we decided to look at offense crime by weekdays. So here we have a chart that is showing offense crime based on the based on weekdays. And one thing that we notice is that Friday has the maximum number of offense count, while Sunday has the least number of offense count, which is actually about 10% less than the crime that we found out on Friday, which is where we have the highest number of offense or crime. So I think it makes sense because Sunday is more like a religious day where people are resting. So we're not seeing a significant number in offense or crime. Then Friday is more like a social day. People are going out after work, some are traveling for weekends. So it could be the reason why we're seeing this increase on this particular weekday. Next to Friday is Monday. So there's also a rise in crime on Monday and then Saturday, Thursday, but Tuesday and Sunday, we're seeing the number of crime or offense drop. So next, we decided to even go further to break down the analysis. So we looked at offense or crime count per hour on hourly basis. So here the x-axis is showing the showing the time in is showing the hourly time. So we have from 1 until up until 23, 0 is 12 midnight. Then on the y-axis we have the number of offense or the crime count. So here we see a significant increase of offense count on around 1 a.m. and 5 a.m. has like the least number of offense or crime count. Then we also notice that 3 a.m., 4 a.m. are not as high as the other hours of the day, and so we're seeing that majority of the crime or offense occurs around 1 a.m. It's very significant, and next to it is 2 a.m. Then another thing we noticed again is that from 8 p.m. to up until 11, like we still see crimes occurring, offenses occurring, but it's not as high as what we saw in 1 a.m., 12 midnight, and 2 a.m. So still looking at the times, we also try to understand or see the offense crime across seasons. So here we have winter, which is December to February, summer, which is June to August, spring, which is March to May, and autumn, which is September to November. So one thing that we noticed in this analysis is that the summer season has like the highest number of offense or crime in the city of Houston, and this makes a lot of sense because the weather is very good. And then we're seeing the autumn has like the least number of offense crime, which is about 9% less than what we saw in the summer season. So next we have our label creation. We had the NIBRS code, and then we also calculated the crime number and each crime type based on the number of day and then seasons. Then, like I mentioned earlier, we had to merge the weather and the crime data set together, and we merged it with the dates because the date was a common variable in the crime and the weather data set. So here is a link that is providing the shows where the data is stored for the model development team. So next, we had to also carry out some bivariate analysis on the weather data. So one thing we noticed is that we see an important number of crime when the humidity is around 60 to 80%. Then we also notice a significant number of crime or offense when the temperature reaches about 83 to, when the temperature is between 83 and 85 Fahrenheit. Then crime is not much when it's snowy or raining, which makes sense. I guess the weather is not convenient for the offenders. Then still on the weather data. So during the analysis, the next thing that we noticed is that the crime rate is very high when the visibility is at its highest. And crime rate also reduces when visibility is reduced. So we see a relationship between crime rates and weather here. Then another thing we saw is that the dew also impacts the rate of crime, similar to the temperature. So we noticed that there's a positive correlation between the dew and the temperature in case of the impact in crime rates. So here is a summary of the bivariate analysis for temperature, still on the weather data. So we looked at some variables. We had the F statistics and the p-value, and with ANOVA, we see that there's a significant difference in temperature across various weather conditions. So because of this significant difference and relationship, these variables were also included as part of the model development variables. Then we also looked at Pearson correlation coefficient to understand the collinearity between some of the weather variables. And then we see that there's a collinearity between temperature and some temperature related features. So this is all we did for exploratory data analysis for this particular project. And I would just like to mention some of the collaborators that participated here. We have Tasco, Lidpova, Udo, Sabine. Then our collaborators, we have Miho, Satish, Dihya, Ahmed, Mary, Min, Tariq, Aisha, Saha, and Mark. So I'm going to hand over to the model development team now.
Okay, Udo. And Agatha, please go ahead.
I hope you can see my screen.
Yes.
Perfect. Then as we approach the model development phase of our project, we stood at pivotal juncture in our mission. Our objective remained unwavering to employ data-driven insights to fortify the safety and security of Houston community. And ideally, we hoped to develop a model that would predict accurately results in the margin of error of 20%. The critical stakeholder of the project was Houston Police Department. In this phase, signified the culmination of rigorous analysis and strategic preparation as we meticulously crafted predictive models precisely attuned to nuanced interplay of crime and weather in the dynamic landscape of Houston. Throughout this project, we explored various approaches, including classification and regression models, to unravel the intricate relationship between crime and weather dynamics in Houston area. However, after careful consideration and rigorous evaluation, we ultimately decided to approach this problem using a time series analysis framework, as it aligned best with our objectives. In this presentation, we focused on 3 models with exceptional promise in forecasting crime in the midst of changing weather patterns. Sorry, because so as we decided to delve deeper into time series analysis models, we tested multiple different models, ranging from classical time series techniques like SARIMA to advanced machine learning models like LSTM and EBM that cover a spectrum of capabilities. They are tailored to handle various aspects of time series data and offer a versatile toolkit for forecasting tasks. Each model was designed to predict the daily crime count and specific crime types count, serving as our target variable. The models were tailored to leverage 3 k-sets of independent variables, which would be weather, lagged crime count, and temporal data. To evaluate the performance of these models, we consider the following metrics: mean absolute error, mean absolute percentage error, root mean square error, and R-squared. This comprehensive approach allows us to thoroughly assess the effectiveness of each model in forecasting crime rates. After analyzing a lot of different models, 3 models perform better than others. In subsequent slides, we introduce those 3 models that will be VAR, light GBM, and EBM models. Each model was chosen for its distinct strengths in predicting crime within dynamic weather conditions, collectively forming a powerful toolkit to enhance public safety. On our journey through VAR illuminated the effectiveness of multivariate time series analysis, shedding light on the intricate relationship between crime, weather, and other factors. Light GBM, with its proficiency in handling vast datasets in nuanced feature interactions, further amplified our predictive capabilities. Finally, EBM model, an interpretable model, furnished us with lucid and actionable insights, empowering us to make informed decisions. While each model brought invaluable contribution, we ultimately select one for deployment, and that would be the EBM model, which we believed held the highest potential in enhancing our objective. Let's delve into the distinctive advantages of the vector regression model, VAR. A powerful in our time series analysis in our exploration of crime prediction. VAR stands out for its proficiency in concurrently analyzing multiple time series variables. This capability uncovers intricate relationships that might otherwise remain concealed. One of the distinctive features of VAR is its consideration of lagged variables. In this model, each variable's current value isn't solely influenced by its own past values, but also by the past values of other pertinent variables. The comprehensive approach ensures a thorough understanding of the interplay between different factors. Moreover, VAR introduced the concept of the bidirectional modeling, recognizing the existence of feedback loops within the system. This means variables can exert influence on each other in both directions, offering a more nuanced perspective on the underlying dynamics. To maintain model integrity, VAR operates under the assumption of stationary time series. This crucial assumption ensures that the statistical properties of the time series remain consistent over time, providing a foundation of reliability and accuracy for our predictions. One of VAR's key strengths lies in the forward-looking capability. By leveraging historical data and lagged variables, VAR empowers us to make precise predictions about future values. This proactive approach is invaluable for informed decision-making. With these key advantages, VAR emerges as a robust model well-suited to tackle the complexity of our time series analysis. Its ability to capture intricate relationships and predict future values position. It is a pivotal tool in our forecasting endeavors. In the process of building our VAR model, one of the critical steps was selecting the right features. The decisions significantly impact the model's accuracy and effectiveness. Here's an overview of our feature selection process. We can see on the left top plot the total offense count and top 3 crime types. These were chosen as our target variables. They provide a comprehensive view of crime trends in Houston. Total offense count is an overarching metric providing a comprehensive overview of criminal activity, allowing us to grasp the overall trend and patterns. Top 3 crime times let us understand the dynamics of the most prevalent type of crimes, including, in this case, burglary / breaking and entering, assault offenses, and larceny / theft offenses. It's pivotal in developing effective crime presentation strategies. And as the focus is on weather-related features, we conducted the Granger's casualty test and selected weather-related features with the p-value less than 0.05. This ensures that our model incorporates only relevant weather data that has a significant impact on crime rates. By focusing on these K variables, we refined our model to capture the most influential factors in crime prediction. This strategic feature selection process was pivotal in enhancing the model's predictive power. In the development of VR model, next crucial step, known as feature transformation and inversion, was undertaken. This process plays a pivotal role in refining the model's predictive capabilities. Here's a closer look at what we accomplished. We began by subjecting assault offenses and offense count to the augmented decay Fuller test. This test assesses the stationarity of a time series, a crucial assumption for accurate modeling. As a result, we successfully differentiated these variables. To ensure uniformity and comparability across features, all variables were subjected to min-max scaling. This process optimizing the range of our variables, enhancing the model's performance. To validate our forecast, we undertook the process of forecast inversion. These crucial steps allow us to compare the predicted values with the actual observed values. By meticulously executing these steps, we fortify the foundation of our VR model, ensuring it is well prepared to deliver accurate and reliable crime forecasts. On this slide, we can see the evaluation of our VR model. We observe some interesting trends, specifically for the forecast of assault offenses. We were able to accurately capture the underlying trend. However, as we extend the forecasting horizons, we noticed a slight decrease in forecasting accuracy. Taking a closer look at the metrics table, we can see that as we project farther into the future, the VAR model experiences a subtle decline in its predictive performance. For instance, when we consider a 7-day forecast, the mean absolute percentage error stands at 0.09. This means our forecasts are quite accurate for this time frame. However, when we extend the forecast to 31 days, we see a slight decline and higher MAP to 0.11. While this indicates a small decrease in accuracy, it's important to note that our model is still providing valuable insights. These findings highlight the importance of carefully considering the forecasting horizons when using VAR model. It's a crucial factor in ensuring the reliability and usefulness of our predictions. On the next slide, that looked fairly similar, but it's focusing on the assault offense forecast. The previous ones focused on the assault offense forecast. Here we're focusing on the offense count. And what's intriguing, we continue to observe the trend that aligns with our earlier findings. Just as we saw with the assault offense forecast in the previous slide, offense count accurately captures the prevailing trend, reinforcing the reliability of our model. However, it is noteworthy that we noticed a similar flattening in the trend after August 14. This consistency across different offense types underlines the robustness of our VAR model in detecting and reflecting critical shifts in crime patterns. Yet, it is essential to acknowledge that as we extend our forecasting horizons, we do notice a slight dip in predictive accuracy. This echoes the pattern we observed earlier, underscoring the importance of careful consideration when choosing a forecasting time frame. For instance, for 7-day forecast, we observe a MAPE of 0.13, indicating a commendable level of accuracy. When we project farther into future with a 31-day forecast, we see a modest uptick in MPE to 0.2. While this signals slight decrease in precision, it is crucial to remember that our model remains a valuable tool to providing timely crime forecasts. These consistent trends affirm the efficiency of our VRR model and further validates its potential in enhancing an understanding of crime dynamics. Understanding these nuances empower us to harness the full potential of VAR model in our crime forecasting endeavors. The second model that we would like to discuss in a little bit more details is the LightGBM model. Let's delve into key advantages of that model. Firstly, LightGBM employs a technique called boosting with residuals. This means it focusing on refining predictions by paying extra attention to the areas where previous models had some difficulty. This iterative process leads to a more accurate forecasting tool. Next, LightGBM utilizes the strategy known as effective bagging. This involves training multiple models on different subsets of the data and then combining their predictions. Notably, LightGBM applies this technique not only to different samples of the data, but also to different sets of features. This comprehensive approach makes the model more robust and stable in its forecasts. One of LightGBM's standout strengths is its ability to achieve high levels of accuracy, especially when dealing with large and complex data sets. Its advanced algorithms and ensemble learning techniques allow it to capture intricate patterns and relationship within the data, resulting in more precise forecasts. Furthermore, LightGBM is highly resource efficient. This means it performs exceptionally well, even in scenarios when computational resources are limited or where real-time forecasting is crucial. Despite its efficiency, LightGBM doesn't compromise on accuracy, ensuring reliable forecast even in a resource-constrained environment. With these combined strengths, LightGBM emerges as a powerful tool in a time series analysis. Its capabilities in accuracy, stability, and efficiency make it an excellent choice for a wide range of forecasting applications, including predicting crime trends, aligning seamlessly with our objective to enhance public safety in Houston. In the evaluation of our LightGBM models, we undertook a comprehensive approach. We conducted a thorough grid search for hyperparameters and implemented time series split cross-validation, allowing us to meticulously fine-tune the models. The results were compelling. We generated two sets of predictions, one with weather information integrated and another without it. This enabled us to discern the impact of weather on our forecasts. The accompanying plot paints a vivid picture of the performance. It shows the time series of actual data overlaid with predictions derived both with and without weather features. This visual representation provides a clear perspective on the model's accuracy. Additionally, we quantified our findings. The table highlights different evaluation metrics with the mean absolute percentage error for both scenarios. With weather information, we achieved an impressive low MAPE of 0.054. Even without weather, our model demonstrated commendable accuracy with MAPE of 0.056. This meticulous evaluation process reaffirms the effectiveness of our LightGBM models, underscoring their capability to reliably forecast crime trends in Houston. In our analysis of the LightGBM model, we delved into the intricacies of features importance. This bar plot visualizing the significance of different features, shedding light on their respective contribution to the model predictions. To unravel the why behind the importance score, we turn to the SHAP, Shapely Additive Explanations module. This powerful tool allowed us to explore both global and local interpretations of the model's decisions. By understanding how features impact predictions on average across all instances, we gain invaluable insight into the model behaviors. One of the key strengths of SHAP lies in its mathematical foundation. These foundations ensure the reliability and consistency of feature importances. Inconsistency in importance scores can be problematic, potentially leading to unreliable model assessments. However, SHAP values remain steadfast in their results, regardless of feature order or the inclusion of irrelevant features. Now let's focus on the weather factors. Among this, maximal temperature emerged as the most influential feature, with the importance scores of 0.01. It's worth noting that we synthesize the collective importance of all weather-related factors, encompassing temperature, precipitation, conditions, moon phase, wind, solar, and more. These thorough examinations of features' importance empower us with a deeper understanding of the model's decision-making process. It provides us with valuable insights that not only enhance the model transparency, but also guide us in refining our crime forecasting capabilities in Houston. Further in our evaluation of light GBM models, we explore the impact of weather information on crime prediction. Through rigorous experiment and cross-validation, we gain valuable insight. For example, as we can see on the slide, for motor vehicle theft, we observed that inclusion of weather data may introduce slight variation in predictive accuracy. It's noteworthy that weather factors can induce larger errors in the specific category, potentially leading to decrease in overall model accuracy. Similarly, in our analysis of larceny, theft, and assault offenses, we found the weather information plays a subtle role in model performance. This finding underscored the nuanced interplay between weather and crime, offering us valuable considerations as we fine-tune our crime forecasting models for Houston. In our depth analysis of feature importance, we uncovered intriguing insights into how specific weather factors influence different types of offenses. First, let's focus on precipitation and wind speed. We observed a compelling trend. Increasing levels of precipitation and wind speed were associated with a decrease in larceny and theft offenses. This suggests that adverse weather conditions may act as the deterrent for this type of crimes. On the other hand, when it comes to temperature-related factors, we found a distinct pattern. Higher values of temperature-related features corresponded to an increase in assault offenses. This indicates that as temperature rises, so does the likelihood of assault-related incidents. To visually illustrate those finds, we have two insightful plots displaying SHAP values for feature importance. The first plot sheds light on how precipitation and wind speed impact larceny theft offenses, showing a notable negative correlation. The second plot emphasizes the correlation between temperature-related feature and assault offenses, underlying the seasonal nature of these incidents. By dissecting these relationships, we gain a deeper understanding of how weather variables interact with specific crime times, providing us with valuable insight for refining our crime forecasting models in Houston. The third model that we would like to present is the EBM model, explainable boosting machine. Let's delve into the key advantages of it. First and foremost, EBM prides itself on being an interpretable machine learning model. This means it provides us with the clear and understandable insights, which are absolutely crucial for informed decision-making. We can trust that the model's outputs are not only accurate, but also comprehensible. Another notable feature of EBM is its sequential featuring training. Unlike some models that tackle all features at once, EBM takes a deliberate approach by training on one feature at a time. This ensures a focused analysis of individual variables, allowing us to truly understand their impact. EBM also takes into account pairwise interactions between features. This means it considers how different variables may interact with each other, capturing nuanced relationships that might otherwise be overlooked. This level of details is invaluable in uncovering complex patterns within our data. In terms of efficiency, EBM employs lookup tables for rapid predictions. This makes it an excellent choice for real-time application, where quick decision-making is of paramount importance. Even in scenarios where time is a critical factor, EBM doesn't compromise on accuracy. Lastly, EBM offers us the ability to visualize feature contribution. This means we can easily understand the impact of each feature on our predictions, providing further transparency into the model's decision-making process. Overall, EBM is a versatile and powerful tool, combining accuracy, interpretability, and efficiency to enhance our time series analysis. Its unique strengths equip us with a reliable tool for a wide range of forecasting applications. From enhancing crime rate predictions in response to changing weather patterns to refining public safety strategies. In evaluating our EBM model's performance, we implemented a rigorous testing approach. We employed time series split cross-validation, where 80% of our training data was used for validation and remaining 20% was reserved for testing. The visual representation of our model performance is depicted in the time series plot, which showcases the actual and predicted daily crime counts. This allows us to assess how well our model aligns with the real-world data. In comparing our models, we found that the daily crime count light EBM exhibits a slightly better performance compared to EBM. On the other hand, when it comes to forecasting assault offenses, EBM demonstrates a slight edge in accuracy. This insight provides valuable guidance in selecting the most suitable model for specific forecasting needs. Depending on the nature of the crime being predicted, this comparative analysis equips us with deeper understanding of how our models perform in real-world scenarios. In the next step, we analyze the feature importance and local explanations. In our EBM model, we focus on predicting the daily total crime count, a crucial metric for understanding overall crime trends. To achieve this, we delved into the importance of various features in our model predictions. Our analysis revealed that among the features, lack the data took precedent, followed by temporal information and then weather-related factors. This hierarchy provides key insights into which aspect exerts the most influence on our predictions. When it comes to weather, two factors stood out as particularly significant: solar radiation and sea level pressure. These variables played a substantial role in shaping our model's forecast. To gain a deeper understanding, we examined both global and local explanations. The global term feature importance bar plot gives us a comprehensive view of the overall impact of each feature. For individual predictions on unseen data, we delved into local explanation. This process helps us understand why the model made specific decisions for particular cases. Interestingly, we observed that the intercept with the value of 475 held substantial sway in guiding predictions towards the mean value. It is worth noting that while a feature may hold high importance, it doesn't necessarily lead to large prediction value. This underscores the nuanced interplay of various factors in our model. Moreover, EBM takes into account how features interact with one another, further influencing prediction. This intricate consideration of feature interactions is a crucial aspect of our modeling approach. In summary, our investigations into feature importance and local explanations equip us with deeper understanding of how our EBM model operates on both global and individual level. This knowledge is invaluable for fine-tuning our crime forecasting efforts in Houston. In our pursuit of understanding the forecasting crime, we delved into the critical role of historical and temporal factors. Those elements provide essential context for comprehending crime trends. We employed a visual representation transforming each feature into a lookup table. This method empowered us to translate historical data into actionable insight with precision. Incorporating holidays, we made significant observations. On holidays, we noted a decrease of, on average, 44 incidents compared to non-holidays periods. This highlights the substantial impact of public holidays on crime rates. Moreover, specific days of the week demonstrated distinct trends. For instance, Fridays witnessed an increase of 20 incidents compared to the average, underscoring influence of the impending weekend. Conversely, Sundays saw a reduction of 16 incidents, indicating a different dynamic. Aiding our analysis, we considered additional insight. Topmost, the lag 1 of the target to target prediction daily crime count provided valuable context. For instance, if yesterday recorded 700 offenses, today's prediction would increase by approximately 20. When examining the influence of time lags, we unearth intriguing patterns. Prediction based on lags 1 to 7 days exhibited a diverse range, showcasing the dynamic nature of crime trends over time. Yearly trends emerge as another critical aspect. We discerned a gradual uptick in criminal activity, signifying an evolving landscape that demands close monitoring. The histogram geographically displayed the distribution of the plotted feature at the bottom. The yearly trend for the daily crime count was illustrated, giving us further understanding. This meticulous examination of historical and temporal factors equipped us with invaluable insight into underlying patterns of criminal activity. And with this knowledge, we stand poised to make more precise and informed predictions, ultimately contributing to a safer and more accurate Houston community. And when it comes to our weather factors, as we explored their impact on crime rates, it is essential to be mindful of overfitting. As a phenomenon where a model may focus on noise rather than a broader trend. This can potentially affect the accuracy of the prediction. Now, let's turn our attention to specific weather variables. In the process of developing all the models, we discovered that solar radiation, when solar radiation levels increase, we observe an initial rise in daily crime count. However, beyond a certain point, further increments in solar radiation lead to subsequent decrease in crime rates. In temperature, unlike a straightforward linear relationship, higher temperatures exhibit a complex, non-linear impact on daily crime counts. Precipitation shows fascinating trends. As rainfall increases, there is a corresponding decrease in daily crime counts. This reduction can be quite substantial, potentially reaching as low as -100 incidents. Conversely, reduced visibility due to conditions like fog or mist is associated with an increase in daily crime counts. This suggests that adverse weather conditions impacting visibility could potentially lead to up to 20 additional incidents. This nuanced observation offers valuable insight into the intricate interplay between weather variables and crime rates. This understanding enables us to refine forecasting models, providing more accurate and actionable prediction. And finally, as an outcome of our model development, we can see that we actually successfully managed to identify crucial weather-driven factors influencing crime rates. We also identified the importance of different types of features for the crime rate predictions. We also managed to achieve the daily crime predictions within the margin error of 20%. And our model demonstrates effective forecasting capabilities for daily crime counts. So just to sum it up, we can see in the feature importance on the right side of the slide that the most important for the prediction were lagged crime counts, then temporal features, and on the third place, weather factors with the solar radiation, sea level pressure, UV index, temperature, and precipitation and visibility as most important ones of them. And that would be it from the model development. I will pass the screen to the deployment.
Hi, thanks Agada for the wonderful presentation. So hi everyone, my name is Chin Hao Zach, you can call me Zach. So I'm the task co-lead for the model deployments together with Milan Kumar and also Sakrishna, and also not forget one of our collaborators, which is Sabit, which contribute his effort in this model deployment. So without further ado, I will just straight away to dive in. So our goal here is to deploy the machine learning model that is built by our machine learning development team to provide an interactive platform for visualizing and forecasting crime rates in the correlation with weather data. So as you all know, model deployment is a very crucial steps that transform the machine learning model from a concept into a practical tool that can be accessed to a broader audience, so they know that what the models that we are building, they can understand the impact of the model that we are building. So before I dive into the model deployment, so I would like to introduce you one of the tools that we use for this model deployment, which is called Gradio applications. It is an engine that drives our interactive platform. So Gradio apps makes deployment machine learning models easy because it is fast, easy to set up, and it can be seamlessly embedded in the Jupyter Notebook. And one of the highlight also is it is available to deploy the multiple model using the Gradio application. So if you're curious to explore more about it or use it in your further others projects, you may use the link below to refer to these Gradio applications. So I would like to just briefly talk about our deployment process. So and also introduce our web application. So the web applications features two tabs. One is the home page, which is just a brief introduction of what we are doing. And another one is called the EBM prediction, which is we use the EBM models. We deploy the EBM models in one of the page and visualize the predicted result using the EBM models. So currently our deployment focuses on single model first. Of course, we plan to explore more models portfolio in the near future, where we can include as presented by Agata just now, the light GDM model, as well as a VR model to include it, and also let the users or others broader audience to see the predicted crime rates. So another introduction is our model has been trained up to July 31st, 2023. So making the data available for visualization for August and also September. But unfortunately for October, which is the current month, isn't accessible yet due to some missing value in the weather's data sets. So the visualization is currently organized by month, so meaning that you are able to select August or September to visualize the predicted crime rates data using the EBM models. But of course, in near future, when the weather's data set has been more and more increasing, and the year is more and more increasing, we will also enhance the provide to segregation by both month and year. So this is just a pretty code snippet for our models. So because as I mentioned just now, it is fast and easy to use. So you can see at the top left, the coding part here is, you just import a Gradio as a GR, and it just about it. And then you can start to use the Gradio app, and you just create a new function for it. And the third screenshot, as you can see at the bottom here, is just a few lines of codes. You are able to have the Gradio apps deployed, which is the functions, the input, which is drop down, and the output, which is a plot, and the table, which what Gradio is interface here is plot data frames. So this is just an example screenshot of what the data models are, what our deployment web application looks like. So I will just share, let me just share the real Gradio applications to have a look for you. Yeah, I think so. I believe you all can see the Gradio application here. So as I mentioned before, we have two tabs. One is called homepage, and another one is for EBM prediction. So the homepage is just basically a brief introduction of our project background, and also link to our project, which is the Omdena Houston Challenge project. And yeah, I think it's not far, sorry. So the other one is a more exciting part is the EBM prediction. So as you can see here, I'm selecting the August month. So you can see here the output is a graph for the predicted versus the actual reading of the graph. And below one is a table of the predicted and actual value based on the August crime rate data, as well as the residual, which is the actual crime rate minus the predicted crime rate. So all the details are available here. That is for August data. So for September data, unfortunately, we only have the predicted crime rate because the Houston Police Department hasn't updated the actual crime reports for the September 2023. So yeah, that's something we will just follow up to include in our futures. So I mean, based on the application here, we are noticed that we are able to segregate by month, as I mentioned, and check all the predicted value according to using the EBM models until the last one. And I believe one of my co-lead Krishna would like to share his web application also. So Krishna, would you mind to share your screen? Just and take over the presenter.
Just a second. Yes. I think you have to yield your, yeah. Can you guys see my screen?
Yes.
Just a second. Yeah, I basically created the same application using Streamlit, but I'm unable. There are some bugs in model forecast section. I will fix it and update on the Slack. And in the documentation, you can see that entire presentation. I have displayed the entire presentation here. Now, first, I have thought that we will create different pages for different tasks like data development, model development, and data processing and knowledge. But I have just created the page for presentation. Once I have completed, I will share I will mention in the Slack meeting, Slack app. I think
Yep.
that's it
Thanks,
from,
Sakush.
yeah.
Yep. So basically, what Sakrishna is talking, is showing is he is deploying the models in Streamlit. So there are different way of deployment, but this is our approach where both of us just deploy our models either in Streamlit or Gradio. So I think that's all from the tasks from model deployment. So over to you, Xuanqing, for the last part.
Okay, thank you, all speakers. Here's we are going to conclude the potential future work to do in the project. First, in the data collection task, we can create a data pipeline to automatically collect and process new data generated every month. And then for the exploratory data analysis, we can do more feature selection and dimension reduction while we continue optimize our feature used for the model development. And for the model development part, to improve the model improvements, and we need some additional data to get a specific statement regarding the weather and crime relationship. And we can also conduct statistical testing on whether the crime improved the crime prediction, since currently it's a deterministic value. Last, for the deployment, we can write production-ready code that automatically retrains the model by schedule using the modular programming CI/CD pipeline and ML flow to track the experiments. So last, we'd like to end with some concluding remarks. First, crime count can be treated as a time series prediction problem, and weather factors slightly improve the weather forecast, the forecast of daily crime count from the baseline model using only the crime history by 3.6% in mean absolute percentage error. And the glass box model explains how features of crime history, time-related, and weather factors yield the final prediction additively. And the ML model demonstrates that certain crime types are affected by weather factors in a positive or negative way, and temperature affects crime rates to some degree. And this is the project of our repository, including the data and the code we use. And if you have any question or suggestion or collaboration, you can contact me. And that's all. Thank you for your attention. So do we have